Hi, I'm Ben-Yaakov. This presentation is entitled Howland, Deboo, and the non-inverting operation amplifier integrator. Now, the classical circuit of a integrator, operation amplifier based integrator, is shown here. We have a capacitor between the negative input and the output. We have a series resistor. And in this case, if we have, say, a step here, we're going to have an output, but there is a polarity reversal. That is, the output will be negative. This, of course, is not compatible with single supply circuits in which you have a single supply. Everything is positive. You cannot generate a negative voltage, so you cannot use this type of an integrator. There is a solution, which is shown here, based on sort of a matched network here. There's an R and R, C and C. It works. It's a differential type of a integrator. But the downside is that you have the matching of these two sides here. And also, if you need a reset, then you need two switches, both here and here, in order to reset to 0. So this is less convenient, and I'm not going to discuss it. A more useful circuit is this one, which is named after Deboo, and there is a paper that he published 1967 in Electronic Design, a novel integrator result by grounding its capacitor. So here we have the capacitor grounded, and this is a non-inverting integrator. That is, if you have a step here, then the voltage will rise positive and not negative, and of course this will be compatible with a single supply circuit, single supply operation amplifier, etc. Now, although it is named after Deboo, actually this circuit originates with Howland, and I'm going to discuss it a little bit later. So let's first of all see what is the principle here, and in particular the relationship that we need between these resistors, or I should say these resistors, in order to get the proper operation. Okay? So the first thing I'm going to do, I'm going to ask what is the input impedance when I look into here. Okay? So I'm looking into here, and I'm trying to get the input impedance. To do that, first of all, I realize that if this thing is operational and stable, then the voltage between the input terminal is approaching 0. So this point here will be the same voltage as here. Okay? Now this voltage here is a result of this V out after a voltage divider. So we have here VC is V out times this voltage divider, R1 over plus R2. Here it is. And then I can express V out as a function of VC, just reversing it. And then I can find out what is the input current here. The input current will be the voltage here minus the voltage here divided by R3. Here it is. And now if I place V out, replace it by this expression here, then I find that the input current is this expression, which comes out to be here with the negative sign. This means that actually current is becoming out rather than getting in. And therefore, if I look now at the resistance, which is the voltage over the current, I'm getting this expression. So what I find is that the input impedance actually is the resistance, which is negative resistance of this value, R1, R3 over R2, R1, R3 over R2. So this is the impedance that I see here. This means that the circuit now from the input side looks something like that. We have the input, we have R4, and then we have a negative resistance here. Okay? So this is like a simplified circuit after realizing that for a given R1, R2, and R3, I have here this negative resistance seen from here. Now, I'll assume for balancing that R1, R3 over R2 is equal to R4. Okay, so this here is equal to R4. So then I'm going to have R4 and minus R4. I'm doing this because if you have this situation, we'll see it in a minute, the impedance that you'll see here, the internal resistance, is infinitely large. So let's have a look at it. Again, I'm assuming that this is equal to R4. So now I'm going to use the Norton equivalent circuit theorem in order to replace this circuit by a current source and internal resistance. To get the current source, I'm shorting it out here, and then I see that the current here of the short is V in over R4. V in over R4 is the current source. To get the internal resistance, I'm shorting the input voltage and looking into this point. Then I have here two resistors in parallel, R4 and minus R4. This comes out to be minus R4 squared over R4 minus R4, and of course this brings about a resistance of infinity. So what we see here is that we are going to have a current source in the order of magnitude of V in over R4 and an infinitely large internal resistance. That is, the equivalent circuit that we see here around the input by a Norton representation is a current source, very large resistor, infinitely large in the ideal case. So this is an integrator. Okay, so this explains the operation here. Now to get this, we need that R4 will be equal to this, or if you look at it in a different way, you see R2 over R1 is equal to R3 over R4. R2 over R1 is equal to R3 over R4, meaning that this bridge here has to be balanced. Okay, it's a balanced circuit, and this is the condition to get a perfect integrator. By this we are going to get an internal resistance here, which is infinite, and a current source V in over R4. So the question is, can we explain what is really going on here? Well, we found all the derivation, very nice. We have the expression. What is really going on here? So we see that in the balanced case, we have here a bridge, and since it is balanced, the relationship between V out and V epsilon is such that the transfer function between the output and V epsilon is zero. Because if you have a perturbation here, the voltage you'll see here, the input will be zero due to the fact that this is the balanced bridge. So if you now put here an input, okay, there's an input here, V out by itself cannot balance it. The way to balance it would be like having an added voltage here. This can bring back the circuit to a balanced situation, so it will not be saturated. Or if I draw here a current, this is like an equivalent to a voltage drop here, and this is also the way. And this is in fact the principle. That is, this current is balancing out the perturbation of V in, which V out by itself cannot correct. So a current will be generated here to correct and bring the input voltage back to zero. Now this concept was actually first invented by Howland. He was talking about a current source, or a current pump, he called it. That is, we have here a circuit, and you can put here any impedance that you wish, and the current here will be controlled by the circuit as we have seen before. Now in the case of an integrator, this is a special case in which this impedance is a capacitor. So you might say that Howland is the first inventor of the circuit, while Deboo actually implemented it as an integrator. So the question now is, how good must be this matching here? How good must be the matching here? That is, we understand that we need this, but obviously there is a finite accuracy to the resistances. There's a change in temperature. So the question is, how important is the matching and to what level do you need it? Now, we have to distinguish here between two cases. In one case, the matching is such that there is now a residual transfer between V out and V epsilon because of the mismatch, but it is a positive transfer. That is, this transfer is larger than zero. That is, the increased voltage here will increase the voltage here between plus and minus. Now, this is positive feedback. This is a no-no. If you have this, the circuit will not be stable. It'll run away. So you cannot allow it. You cannot allow to have a positive feedback in this circuit. That is, the mismatch cannot be in the direction of a positive feedback. But it can be, of course, in the direction of a negative feedback. Okay? So what is the effect of an imbalance here? Now, we have seen that the resistance here is the parallel combination of R4 and this expression, which is the input resistance here. We have set it to R4, and in this case it came out to be infinitely large. But if this is not R4, then you find that the resistance is R4, this resistance, the equivalent internal resistance here, which makes it an imperfect integrator, is R4, 1 minus this expression. When balanced, this is 1, and RS is infinity. If it's not balanced, then of course you have some resistance, depending on the mismatch here. So let's take an example. If this is like 0.99, okay, this one is 0.99, then the resistance will be, from here, it will be 100 times R4, because this is 1 over 100, the error. So this means that, first of all, you have to make sure that you're not going into a positive feedback. You can allow a little bit of a negative feedback, but the larger the mismatch, the smaller will be this resistance, and the more imperfection are going to have in the circuit. So let's have a look at some simulation here to demonstrate the point that I've shown. So first of all, I'm going to mismatch it and put here actually positive feedback by making this resistor a little bit larger. Ideally, all these are R, which is 10K. Now this one, now I'm increasing it by 1%. And you see that due to this increase, we have a higher voltage here, of course, due to this divider. So therefore, it's a positive feedback, 1%. Now, if I run it, you see that we are getting into instability. The error starts to increase. This is the voltage across the capacitor. This is the output voltage, and this is the voltage, this is the current of the resistor, and you see that there is a drift here by the positive feedback and actually pushing it eventually into saturation. So this is a no-no, and you should never have a positive feedback due to the mismatch. Now, if everything is balanced, here R, and R, then it works fine. Here it is. You see that this is the excitation. This is the voltage across the capacitor very nicely, and this is the output voltage. Everything works perfect. If, however, I again mismatch it, but now in the negative feedback region, which is okay in terms of stability, but it's corrupting the operation of the integrator, because the resistance now will be not infinitely large, but some final resistance, depending on this error here. I've put a large arrow just to see the effect, and you see it here very clearly. Now you see that we have like an exponential increase due to the fact that we have a resistor which is not infinitely large. This is the voltage across the capacitor, and this is the output voltage. So this brings me to the end of this short presentation. I hope you found it of interest, and perhaps it will be useful to you somehow in the future. Thank you very much.